Okay, so we have a nice working definition of the dot product of two vectors. And it's right here. U dot v is the magnitude of u times the magnitude of v times the cosine of theta, and that's going to give us a number, as I just mentioned. It's going to give us a scalar, but we can only apply that definition if we have basically visual graphical representations of our vectors. We can see what the magnitude is, and then we can measure the angle between them. But what if we don't know what the angle between the two vectors is, and we don't want to take the time to figure it out? I tell you what would be nice is if we had a component form of dot product. And that's what we're going to develop right now. This is developed in your text as well, but I think it's worth going through. I'm just going to do it in the two-dimensional case. So let's take a couple of vectors. We'll let them be A and B in this time. So let's let A be a vector that has components. Remember, we can write them this way, A1 and A2. And we'll let B be a vector with components B1 and B2. So a couple of two-dimensional vectors, but everything I do here will be applicable to three dimensions as well. In fact, to any dimensional space that you would like. Of course, we know then that A minus B would be written as A1 minus B1, comma, A2 minus B2. Remember how to add and subtract vectors in component form. Just add or subtract the respective components. Now let's go ahead and set up a picture here, a situation of what we got going on. Let's just suppose A looks like this and B looks like this, and so we have some angle here, theta, between the two. And I hope you remember we can represent A minus B by taking a vector that starts at the tip of B and ends at the tip of A. So looks just like this. There is the vector A minus B. And if you think about that, that's A plus a minus B, and so that would be this vector here translated over here. So you can go back and look at the lecture from vectors in 9.2 to justify that again, or you can see it. I think you can work it through. There's A minus B. The point is I got myself a triangle. That means I have the law of cosines. Remember what the law of cosines said? I got some angle here, theta. The side opposite that, the length of the side opposite that, that would be the magnitude of that vector A minus B squared. That's equal to the magnitude of A squared plus the magnitude of B squared. So the magnitude of the two sides adjacent to that angle, the length of those two sides, minus 2 times the magnitude of A times the magnitude of B times the cosine of the angle between them. Remember, this is just the law of cosines, or law of cosines if you're from the Northeast. Law of cosines. Okay, so we've got something we can work with here if we substitute in our components. So I'm going to solve for this. Notice right here, this is our definition of A dot B. Magnitude of A times the magnitude of B times the cosine of the angle between them. So we're going to solve for that. Let's do a little bit of algebra here. I'm going to swing this over and swing that there. So 2 times the magnitude of A times the magnitude of B times the cosine of theta is equal to, well, magnitude of A squared plus the magnitude of B squared minus the magnitude of A minus B squared. Now what's that equal to? Well, the magnitude of A, if A is given by A1 and A2, that's the square root of A1 squared plus A2 squared, and we're squaring that quantity, so that's going to be squared, plus, let's see, the magnitude of B is the square root of B1 squared, whoops, B1 squared plus B2 squared, but we're squaring that. Now, what's the magnitude of A minus B? Well, we have the components right here, so we square those. A1 minus B1 squared plus A2 minus B2 squared. Take the square root. There's the magnitude of A minus B, but again, we're squaring that as well. Let's break it down. This is going to be giving us our component definition that we want. Squaring the square root, of course, that's nice. We have A1 squared plus A2 squared plus B1 squared plus B2 squared minus, okay, so the squaring the square root gives us back what's underneath here. When I square this quantity, remember, we have A1 squared minus a 2A1B1 plus a B1 squared plus A2 squared minus a 2A2B2 plus B2 squared. All right. Distributing this negative sign through, I have a1 squared plus a2 squared plus b1 squared plus b2 squared. Let's see, minus a1 squared. Minus and minus makes that a plus. 2a1b1 minus b1 squared minus a2 squared. Minus and minus makes that a plus. 2a2b2 and then minus a b2 squared. Oh, some nice things happen here, don't you think? Positive and negative a1 squared, a positive and negative a2 squared, positive and negative b1 squared. Hey, look at all that's left here. So let's take inventory. We've got 2 times the magnitude of a times the magnitude of b times the cosine of the angle between them is equal to 2a1b1 plus 2a2b2. Divide both sides by 2, and remember that this is the definition of the dot product, and we get that a dot b is simply equal to the product of the first components, the product of the second components added together. And of course that will translate into higher dimensions. Very simple example here. So if you didn't like all that explanation, that's fine. I think it's good to see that kind of stuff once in a while. Of course, you're just interested in how it translates into examples that will help you do your homework. Let's look at a three-dimensional case. Let's suppose that a is equal to the vector, say 2, negative 1, 4, and b is the vector 3, 5, 7. Say I want to find a dot b. Easy enough. I take the first components, multiply them together, 2 times 3. I should be careful using that dot there for multiplication. That is a very specific meaning. Plus the product of the second components, negative 1 times 5, plus the product of the third components, 4 times 7. And that gives me, again, 6. Let's see, minus 5 plus 28. That's 1 plus 28, or 29. Again, can't stress this enough. This is a scalar or a number, whatever you want to call it. You take two vectors, you get a number out. So here's what the dot product does. It takes something from v3 cross v3, a vector and another vector, this is how we'd write this formally, and sends it to the set of all real numbers. So it takes two vectors, sends it to a scalar. It's a function, takes two vectors, gives you a scalar out. Now, let's suppose we want to do something else. You'll have a homework problem similar to this. Let's suppose we want to find the angle between those two vectors, A and B. To do this, we're going to use both of our definitions of the dot product. The component definition that we just developed, as well as the original definition that we got from the concept of work. Now, we know right away, from what we've done already, that A dot B is equal to the magnitude of A times the magnitude of B times the cosine of theta, but we also know from what we just did, I'm using the same vectors here, that it's equal to 29. So I should be able to find now the magnitude of A, the magnitude of B, and then solve for theta. I think I can do that. Magnitude of A is the square root of 2 squared plus negative 1 squared plus 4 squared. And that's equal to the square root of 4 plus 16 plus 1, that's the square root of 21. The magnitude of B is the square root of 3 squared, which is 9, plus 5 squared, which is 25, plus 7 squared, which is 49. It's a little bit bigger there. See, if it was 50, it'd be 75, and 9 is 84, but we're one shy of 50, so it must be 83. Okay, so what do I know now? I know that replacing the square root of A and the square root of B with what they're equal to, I'm sorry, the magnitude of A and the magnitude of B, I know that 21 times the square root of 83 times the cosine of theta is equal to 29, which tells me that the cosine of theta is equal to 29 divided by the square root of 21 times the square root of 83, which tells me that theta itself is the inverse cosine of 29 over the square root of 21 times the square root of 83, and we can go ahead and plug that into our calculator if we want an approximation of that angle. Of course, we can tell it's going to be acute because we know the cosine of the angle is positive here, so it's going to be acute angle, I'll let you go ahead and put that into your calculator if you like. Just make sure you're giving the answer in either radians or degrees, whatever is being asked for. All right. And so there you have it. Inverse cosine of 29 over the square root of 21 times the square root of 83. In fact, maybe I'll just go ahead and put that in my calculator. That way we can make sure we got the right answer. I'm going to go ahead and look in my mode here. I'm actually in radians. I'm going to switch to degrees. I'll give the answer in degrees. And so I'm going to take, let's take the square root of 21. That times the square root of 83. I'm going to take 29 and divide it by that result. And I get 0.69 for that, so I'm going to take the inverse cosine, so second cosine most likely, and then that answer, and I get about 46 degrees is what I'm getting. So again, it is an angle between 0 and 90. It's an acute angle, and there you have it. Okay, so it's always good to look at a few properties whenever we introduce a new operation. So let's take a look at that. Again, these are found in your text, but it's probably worthwhile just to point out a few of these. And if we take a dot product of a vector with itself, let's think about what we'd be doing there. Magnitude of A times the magnitude of A times the cosine of the angle between them. What's the angle between them? Yeah, it's going to be 0 degrees or radians. Cosine of 0, of course, is 1. So you just have the magnitude of the vector squared. So the dot product of a vector with itself gives you the square of the length of that vector. Now you can also see using either definition that we have a commutative operation. A dot B is the same as B dot A. You can also see, especially using the component definition, it's pretty easy to see that the dot product distributes across addition. So A dot, the quantity of B plus C, is equal to A dot B plus A dot C. This makes sense, right? Because I have two vectors, take the dot product, and so I'd get a scalar here. We can also think about scalar multiplication with dot product multiplication. So I take a scalar times a vector A, dot it with another vector B. That'll give me the same thing as taking the scalar times B and dotting it with A, or the same thing as taking the dot product first and then multiplying by the scalar. So some sort of associativity there with scalar multiplication. And if I take the 0 vector and dot it with any vector, I get the 0 scalar. All right. Now you might want to think, do we have associativity of dot product? It's worth asking. We talked about an associativity with the scalar product and the dot product. Well, it doesn't make any sense. Suppose I have A dot B and I want to see if A dot B dotted with C is equal to A dot B dotted with C. Well, this makes no sense. Think about why that is. Okay, what happens when I take A dot B? What do I get? I get a scalar. I'd then be trying to take a scalar and dot it with a vector. I can't do that because it's the dot product here. So we don't have an associativity strictly of the dot product. All right, one more thing to talk about here in this section, and that is the concept of projections. We use the dot product to talk about projections here, and we'll give you an illustration of what we mean. Let's say we have a couple of vectors. A vector here I'll call A, and another vector here which I will call B. By the projection of B onto A, I have an angle here, theta. What I mean is visually, I start my vectors in the same spot. I'm going to take the end of the vector B and project it onto A. So I'm going to drop a perpendicular onto A, and then I'm going to form the vector that starts at that same place and ends where B would hit if we went straight down. So this vector right here I refer to as the projection of the vector B onto the vector A. And we write this as PROJ of B onto A, projecting B onto A. So A is in the subscript, as you know from your reading. Now, the length of this we refer to as the component, or the scalar component of the projection of B onto A. So if I talk about the length of this vector, we define that as the component, the scalar component of B onto A. So let's think about how we can find this. Okay, I'm going to start by finding the scalar component, because once I have that, I already know the direction of this vector. It's in the direction of the vector A. So I'm going to start up here by finding the scalar component of B onto A. Now, using our illustration here in this angle theta, you can see that this length of this vector here, this length right here, let me just call that D. The cosine of theta is D over the magnitude of B. Let me just write that here. Okay, D being the length, the component that we're talking about. So D is equal to this, which is equal to the magnitude of B times the cosine of the angle between them. Okay, so D is the magnitude of B, cosine of the angle between them. D is just my shorthand for the component of B onto A. All right. Now, what do I know? Well, I know that A dot B, by definition, is the magnitude of A times the magnitude of B times the cosine of theta. And so, dividing both sides by the magnitude of A, I have that the magnitude of A over the magnitude of B, A dot B divided by the magnitude of A is equal to the magnitude of B times the cosine of that angle. And what is this equal to? This is the component, the scalar component of B onto A. It's the length of that projection vector. So I know how to find the length of it. The scalar component of B projected onto A is given by the dot product of the two vectors divided by the length of A. So what is the projection? Well, how do we change the length of a vector? Remember, we had problems in the vector section where it said, here's a vector, find one that is in the same direction of, say, length 3. And the first thing you had to do was divide by its length. So here, and then multiply by how long you want it to be. I want a vector this long in the direction of A, in this direction right here. So that's going to be our projection of B onto A. And we're going to say that's equal to our vector A divided by its length. So now we've made it length 1. So we scale A back. Say we bring it back here to length 1. And then I multiply that vector times the length of the scalar projection, which is given by A dot B over the magnitude of A. A dot B is a scalar, the magnitude of A is a scalar, and so we can write this as A dot B over the magnitude of A squared. That scalar then times the vector A. That's the projection of B onto A. Let's take a look at an example just to get the idea of it. Let's suppose I've got a couple of vectors. Let's let just 2 dimensions here, so it's a little bit easier to draw, but everything works the same in 3 dimensions. Let A be the vector 5, 0. Let's let B be the vector 2, 1. Now this should be pretty straightforward here to see what the answer is going to be. 1, 2, 3, 4, 5, 1, 2. So here's my vector A, 5 in the x direction, 0 in the y direction, or 5 in the I direction, 0 in the j direction if you like. B is the vector that goes over 2 and up 1. So here's the vector B. Now we can see clearly what the projection of B onto A is going to be. We drop this straight down, we're going to hit right there. So we can see just by looking at the picture that the projection of B onto A is going to be the vector 2, 0. We're going to use our formulas and see if we can find that. We can also see that the length of that vector, so the component of B onto A, is going to be equal to 2. It's a vector of length 2. So let's go ahead then and start with that component using a formula. The component, the scalar component of B projected onto A was defined to be A dot B divided by the magnitude of A. Is that right? Let's double check up here. Yeah, A dot B over the magnitude of A. Well, that's A dot B, that's 5 times 2. So just using our component definition, plus 0 times 1. Sorry, I shouldn't be using the dot there. Divided by the length of A. That's square root of 5 squared plus 0 squared. And this, the square root of that. So that's 5 times 2 is 10 plus 0. Square root of 5 squared is 5. 10 over 5 is 2, just as we had surmised. Now let's go down here and say, all right, the projection of B onto A by what we had said is going to be A dot B over the magnitude of A squared, all in the direction of the vector A. So A dot B, we know that's 10. Magnitude of A is 5, so we'll take 5 squared. All that in the direction of A, so that's scalar multiplied by A, which is 5 comma 0. That's 10 over 25 times 5, 0. If we multiply that through, 10 over 25 times 5, that's 10 times 5 is 50. 50 over 25 is 2. 10 25ths times 0 is 0, just as we had surmised. So those formulas do work. Okay. Incidentally, though, you can actually project the other way. Let me just show you that real quick. If I wanted to project A onto B, I can do that. Here's how I would do it. I'd have to extend B out imaginary style, drop my right angle. It would be, it would be this vector right here. This would be the projection of A onto B, and you just reverse how it works. Here, this would be equal to, well, it would be A dot B over the magnitude of B squared, all in the direction of the vector B, which that's probably not too hard to figure out. A dot B we know is 10 already. Let's see, the length of B, that's the square root of 2 squared, which is 4, plus 1 squared, which is 1. All in direction, let's see, we're going to square that. The direction of B, which is 2 comma 1. So I've got 10 over the square root of 5 squared, which is just 5. 10 over 5 is 2. 2 times 2 is 4. 2 times 1 is 2. So it's 4 comma 2, and that's exactly what we get. We go out 4 and up 2, and there you can see that's the projection of A onto B. All right, should be in good shape for your homework for this section. The password to get into it. Callithump. Callithump. I mean, that's a good word you can use, especially if you're into music or something like that. It just means a noisy or boisterous parade. A lot of times it's used to refer to a parade or any celebration. So maybe you'll make a callithump after you finish your homework for this section. Good luck on 9.3. If you have any questions, that's Callithump, by the way. If you have any questions at all, please let me know.